the last thing I'd like to cover is um, bring this all back to original research question. But before I do that, I just want to quickly point out, so this is a little bit unsatisfying. You see this steep increase in the recovered population and the steep decrease in infected population. That's because we put in that 18 days of no new infections, means that everyone goes into the recovered population. So it's a step function, and it's somewhat unsatisfying because it should probably look a bit more like this and a bit more like this. But it does help us move in the direction of answering our research question, even though that exact shape is not quite satisfactory, and we should put in some more time to fix that. But let us let us go back up here. This is the 140-day mortality rate. So this is one of the outcome variables that we were interested in terms of measuring the effectiveness of any policy. So I'm just going to cut and paste this down here so it's a little bit easier to see. And so you can see as we adjust the date of intervention, so if we have it at day 60, it's really too late. We've about 2.79% of the population has deceased. The virus has really run its course. Everyone has almost moved into this recovered population. The susceptible population is like 1. It's statistically, 0. So everyone has basically got the disease, and about 3% of people have died. So that's not an ideal outcome for Massachusetts. So if we move this intervention sooner, so let's say day 20, we brought down the mortality rate a bit, a little bit anyway. So that's more effective than if you've missed the peak. If you have all your infections here and you put your intervention here, that's going to do nothing for you. If we move the intervention a bit sooner, let's say day 19, you can see it. We've almost halved, not quite, the mortality rate from just a one-day move on it. Yeah, not quite half at all, but we've had a significant effect on it just by moving it a day earlier. And let's see if we do the 18th. So we go 2 days. So from the 18th, we're at a 1% mortality rate. If we move this to the 20th, we've doubled our mortality rate. So those 2 days are critical in our system. We can have the death rate by just moving it 2 days. So let's try like the 17th. Again, we've halved it, and this is because it's exponential growth. So every day that we move it sooner, the better the results are. That's why interventions in these sort of pandemics is so important that you do it early on, because you can prevent the exponential growth if you catch it early enough, and if not, it's really can get out of control. So in terms of policy advice for Massachusetts, the sooner you can implement something like a near total social distancing, the better. And let's see if we have it at a really pretty good day, like 15 days in from the first infection, but we weaken our measures. Let's see what happens. So I'll go like 0.8. So you've got a higher mortality rate. You can see you've got many more infections, but you've still got about 4 million people have been infected and recovered. About 3 million people were spared any sort of sickness or exposure. So anyway, that is how you can use this sort of model to modify different policy scenarios. How aggressive do you want your social distancing to be? If you do a very weak one, you've essentially done nothing, and that's reflected in your mortality rate. So even though you did it at a good day, you just didn't do enough to make a difference. Okay, so I hope that is helpful in terms of showing you how you can add a variable. Some of the messy workarounds using if statements, and statements, and playing around with the model. But yeah, if you have any questions, feel free to contact Justin, Christian, or I, and have fun. All right. Yeah.